Good morning, all of you. Yesterday, we were dealing with Schrodinger wave equation, that is del square psi by del x square plus del square psi by del y square plus del square psi by del z square plus 8 pi square m by h square into E minus V into psi is equal to 0. E total energy, V potential energy. This entire Schrodinger wave equation is written as H Hamiltonian psi, H psi is equal to E psi. H is the Hamiltonian operator and psi is the wave function. Psi is the wave function for electron, E is the energy. So, H psi is equal to E psi. When we solve this equation, the solutions of this equation gives the values of E and psi. E is the quantized value of energy. E is the quantized value of energy, while psi is the wave function for electron. Psi is the wave function for electron. So, when Schrodinger wave equation is solved for hydrogen atom, first they solved it for hydrogen atom only. It is again a one electron system. The solutions of this Schrodinger wave equation, when Schrodinger wave equation is solved for hydrogen atom, the solutions give the possible values for energy, that is possible energy level, that is n is equal to 1, 2, 3, etc. and the corresponding wave function psi for an electron associated with each energy level. These energy levels and the wave functions are characterized by a set of 3 quantum numbers. Set of 3 quantum numbers, this we have to learn separately. So, these quantum numbers are principal quantum number, Azimuttal quantum number, magnetic quantum number. So, by denoting all these three, we can specify an orbital. You know orbital? Orbital is the space around the nucleus where the probability of finding electron is maximum. So, 3 quantum numbers we will be learning. Principal quantum number, which is denoted by n, that is n is equal to 1, 2, 3, etc. Azimuttal quantum number denoted by L. Magnetic quantum number m or ml. And psi has no meaning, but psi square gives the probability density. Psi square gives the probability density. At any point, probability density at any point. So, when Schrodinger wave equation is solved for hydrogen atom, the solution gave all possible values for E and psi. Energy levels, that is n is equal to 1, 2, 3 and the corresponding wave functions psi for an electron associated with each level. These energy levels and the wave functions are characterized. These energy levels, this n is equal to 1, 2, 3, etc. These energy levels and these wave functions are characterized by a set of 3 quantum numbers. What are these quantum numbers? Principal quantum number, Azimuttal quantum number, magnetic quantum number. So, by telling all these 3 quantum number, you can talk about an electron. To specify a particular electron in this orbital, if you show this orbital by a box, if you represent an orbital with a box, then this orbital can accommodate maximum 2 electrons. To specify one electron in this, you have to specify the spin of the quantum number, spin of the electron also. An electron may spin in the clockwise direction or in the anti-clockwise direction. Let's go to quantum numbers. So these quantum numbers are obtained from Schrödinger wave equation. This gives the complete address of an electron. We know that an atom contains large number of orbitals, and these orbitals are distinguished from each other by their energy, shape, and orientation. Energy. When n is equal to 1, K shell, electron is in the lowest energy level. When n is equal to 2, L shell, electron is in the next higher energy level. In that way, you can talk about the energy of the orbital or energy of the electron. An atom contains a large number of orbitals, and these orbitals are characterized, or these orbitals are distinguished from each other by their shape, size, orientation. Orientation means direction in space. These characteristics are expressed in terms of 3 quantum numbers we said. What are these quantum numbers? N, L, M. Size is given by N. N gives the size. Shape is given by L. L gives the shape of the orbital, and orientation is given by M. Orientation. Size means we can come to know its energy, orbit, or shell. Shape means in this shell N, what is the subshell? What is the subshell? It gives the shape or it gives the subshell of this main shell. M gives the orientation that we will discuss afterwards. Each orbital is designated by these 3 quantum numbers. Each orbital is designated by these 3 quantum numbers. To designate an electron in an orbital, its spin is also to be mentioned. It is given by the spin quantum number. We denote it by S. So each electron in a particular orbital, an electron in a particular orbital is represented by how many quantum numbers? 4 quantum numbers. These 4 quantum numbers. First 3 quantum numbers to designate an orbital, including this 4th quantum number to designate an electron. First quantum number, that is principal quantum number. I told you this is denoted by N. It shows what all things? Size. Size of the orbit or energy of the orbit. Or we say it represents an orbit or a shell. So these things are given by this letter L. Smaller the size, lesser is the energy associated with this. N is equal to 1, smaller size. N is equal to 2, bigger size. N is equal to 3, again bigger size. Smaller the size, lesser is the energy associated with it. Now, this N determines the size, that is energy of the shell or principal energy level. Principal energy level. First shell, second shell, third shell, etc. When N is equal to 1, K shell. N is equal to 2, L shell. N is equal to 3, M shell. Energy increases with the increase of N. Energy increases with the increase of N. You can show it like this: 1, 2, 3, 4. Energy is increasing in this order. Energy increases with the increase of N. And maximum number of electron in any shell is given by 2n square. This you have learned in class 9th, class 10th. Maximum number of electrons in a particular energy level is given by 2n square, where n is the principal quantum number. So in first shell 2 into 1 square, that means maximum number of electrons that can be accommodated in this first shell is 2. In the second shell, again 2n square, that is 2 into 2 square, that is maximum number of electron that can be accommodated is 8. Third shell, 3n square is the maximum number of electrons, that is 3 into 3 square, that is 18 electrons can be accommodated. Maximum, this number is maximum. So n shows the energy, or n shows the size, or n shows the orbit, or n shows the shell or principal energy level. Next quantum number is Azimuttal quantum number. This is denoted by L, and it gives what all things? It gives the shape, or it gives the subshell. It is also called subsidiary quantum number. Subsidiary quantum number. Subsidiary quantum number. This defines the three-dimensional shape of the subshell. Three-dimensional shape. For example, you know, psi square gives the probability density. Wherever there is probability density, I am putting a dot to show that probability. So these dots where I can see electron, the presence of electron is shown by these dots. So it is a diffused situation. You cannot give the exact boundary. And these dots all together, if I visualize, I get the probability density. See, this is called a P subshell. The shape is like a dumbbell, D-U-M-B-B-E-L-L, dumbbell, or Probability density, if I find, that means xi square. Probability density psi square, if I mark, I will be getting like this. There is no clear boundary. It is in the diffused state. This is S subshell, that is spherically symmetrical. S subshell, what is the shape of S subshell? That is spherically symmetrical. And another shape, that is double dumbbell shape. This is the shape of a D subshell. The shape is double dumbbell. So S means spherically symmetrical. The shape is spherically symmetrical. P, that is dumbbell shape. D subshell has double dumbbell shape. So the subsidiary quantum number defines the three-dimensional shape of the subshell. Actually, this explains the fine lines. Fine lines, we know that was a drawback of Bohr model. These fine lines together we call fine spectrum. This azimuthal quantum number or subsidiary quantum number can explain these fine lines. Now this L value depends upon n value, that is the principal quantum number. For a given value of n, now I am starting with n to get L value. For a given value of n, L can have n values ranging from 0 to n minus 1. So for a given value of n, L can have n values ranging from 0 to n minus 1. For example, if n is equal to 1, L can have 1 value ranging from 0 to n minus 1, that is 1 minus 1, that is 0. That means 0 to 0 means only 0. So that is this 1 value. If L is equal to 0, means the 0, we denote this as S subshell. If n is equal to 2, next, when n is equal to 2, L can have 2 values. What are these values? These values are ranging from 0 to n minus 1, that is 2 minus 1, that is 0 to 1, that means 0 and 1, these are the 2 values. One value is 0 and the other value is 1. When L is equal to 0, S subshell. When L is equal to 1, P subshell. S subshell is spherically symmetrical and P subshell is dumbbell shaped. Now, when n is equal to 3, when n is equal to 3, L can have 3 values. Ranging from 0 to n minus 1, that is 3 minus 1, that is 0, 1, 2. When L is equal to 0, S subshell. When L is equal to 1, P subshell. When L is equal to 2, D subshell. So these are the three values 0, 1, 2. Now when n is equal to 4, then one more, that will be S, P, D, F. Then n is equal to 5, S, P, D, F, G, then H, I, J, K, like that. But so many are not there. Till now, elements discovered got the electronic configuration till F only. So n is equal to 4. If the principal quantum number is n is equal to 4, then subshells will be S, P, D, F. Now you see, when n is equal to 1, only S. So we denote this subshell as 1S. Here 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, 4F. In this way, we denote the subshells. 1S, there is no 1P, there is no 1D. 2S, 2P, there is no 2D. 3S, 3P, 3D, there is no 3F, like that. Number of subshell, how many subshells? N. Number of subshell will be n for the principal quantum number n. Number of subshell. If the principal quantum number is 1, then number of subshell will be 1. When the principal quantum number is 2, the number of subshells will be 2. S and P. When the principal quantum number is 3, the number of subshells will be 3. 1, 2, 3. So the number of subshells is equal to n for the principal quantum number n. Next is magnetic quantum number. This gives the orientation or direction, and it denotes the orbital. So N orbit, L subshell, and M or ML, that is orbital. What is meant by this direction? What is meant by this orientation? Due to the motion of electron is a charged particle. Due to the motion of an electron around a nucleus, a magnetic field is created. When an electron moves around the nucleus, a magnetic field is created. And when this magnetic field interacts with the external magnetic field, what is meant by this external magnetic field? That is a magnetic field from other electrons. So one electron, its magnetic field, and all the other electrons together, a combined magnetic field. So when one electron's magnetic field interacts with the external magnetic field, it takes different directions. Magnetic quantum number shows the spatial orientation of the orbital with respect to a standard set of coordinate axes. Suppose this is Z axis, X axis, and Y axis, this is below this screen and this is above the screen. Let this be Y axis. So a dumbbell shaped P subshell can be along Px like this, along Py like this, or along Pz like this. So for Px we show like this, x axis. For Py we show like this, y axis. For Pz like this, that is z axis. This is Pz. So Px, Py, Pz. So with respect to standard set of coordinate axes like px along x-axis, py along y-axis and pz along z-axis. Here for any L value, M can have 2L plus 1 value ranging from minus L through 0 plus L. So for any L value, M can have how many values? 2L plus 1. For example, if L is equal to 0, when does this L become 0? That this L value depends upon N value. Let's start with N. When N is equal to 1, L can have one value, that is 0. When L is equal to 0, M can have 2L plus 1 value, that is 2 into 0 plus 1, that is 1 value. And this value, what is this value? This value ranges from minus L through 0 plus L. That means minus 0 through 0 plus 0 means only 0. That means M is equal to 0. L is equal to 0 means S subshell. M is equal to 0 means the same thing. We call it as S orbital. Now, when N is equal to 2, L can have how many values? 2 values, that is 0 and 1. When L is equal to 0, that is S subshell. Just now we have seen at that time M is equal to 0, that is S orbital. But when L is equal to 1, M can have how many values? That is 2L plus 1, that is 2 into 1 plus 1, that is 3 values. What are these 3 values? That is ranging from minus L through 0 plus L, that is minus L. L is 1, minus 1 through 0 plus 1. So this orbital, this orbital, this orbital. About this we will discuss tomorrow. Thank you.